Lesson 10-4, probability and the multiplication rule. A compound event or a composite event consists of two or more simple events. Independent events are two or more events in which the outcome of one event does not affect the outcome of the other event. So independent, think of two separate events, they don't impact each other. Suppose a coin is tossed and the spinner shown is spun. The sample space for this experiment is you get heads 1, heads 2, heads 3, heads or tails 1, tails 2, tails 3. Using the sample space, the probability of the coin landing on heads and a spinner on 2 is 1 out of 6. There are 6 possible outcomes. Only one of them has heads 2. Notice that the same probability can be found by multiplying the probabilities of each event. Simple events. So probability of H is 1/2. Probability of spinning a 2 is 1/3. 1/2 times 1/3 is 1/6. That would be the multiplication rule for probability. So probability that two independent events both occur is the product of the probabilities of each individual event. So probability of A times the probability of B would be the formula for two independent events. Question 1. Anna is a member of a gaming website that randomly pairs users together to solve puzzles. Of the 50 other players currently online, Anna is friends with 10 of them. Suppose Anna is paired with a player for a game. Not liking the outcome, she disconnects and is paired again. What is the probability that Anna is not paired with a friend in either match? So there are a total of 50 players, and she's friends with 10 of them. That means 40 of them are not her friends. So if I take 40 out of 50 times 4 out of 50, 40 out of 50, because the probability of A is not a friend, probability of B is not a friend. If I multiply those, I can simplify these by dividing by 10. So 4/5 times 4/5 is 16 out of 25. So we keep that as our probability, or if you want to do it as a percent, 16 divided by 25 would be 64%. Letter B, what assumption do you have to make in order to solve this problem? You have to assume that the same 50 players remain in there and nothing changes. And that the people that she's friends with doesn't change. So the number of people and her friends do not change. Next question. Actually, this one, you could also use an alternative method for this one. This one is a little more difficult for that one. You could draw it out. So you could also use an area model to calculate the probability that Anna is not paired with a friend in either match. The probability that a player is not a friend of Anna's is 40 out of 50, which is still 4/5. So if you do 4/5 times 4/5, you're just looking at this piece right here. That would give you your 16/25. The blue region represents the probability of two sequential players not being friends with Anna. The area of the blue region is 16/25. The orange region represents the probability of two sequential players being friends with Anna, and the area of the orange region is 1 out of 25 of the entire region. So that's just another way of going through that. And the easier way would be using the multiplication property or multiplication rule of probability. Next, each week, the lead teacher randomly selects 3 names out of a hat from 24 students in class to help with tasks around the classroom. After each drawing, the names are placed back into the hat. What is the probability that Khalid's name will be chosen 2 weeks in a row. So for the first week, he has 3 out of 24 chances of being picked. They put the names back in, and you still have 3 out of 24 chances. That will give us 9 out of 24 squared, would give us 576. And if you did 9 divided by 576, you get 1 out of 64, or as a percent, that would be 1.5625%. Next, Paula's weather app tells her that there is a 20% chance of rain on Tuesday and a 50% chance of rain on Wednesday. What is the probability that it will rain on both Tuesday and Wednesday? So I can use the multiplication rule of probability. So if I have a 20% chance, that's 0.2 times 0.5, 50%. That would give us 0.1 or 10%. Or if you put it as a fraction, that'd be 1 out of 10. Next, dependent events are 2 or more events in which the outcome of one event affects the outcome of the other. Suppose a marble is chosen from the bag and placed on the table. Then another marble is chosen from the bag. The sample space for this experiment is RB, RB, RR, BR, and BB. So with dependent events, you take one out, there's one less left in there because you're not replacing it. When choosing the first marble, there are 7 possible outcomes. The probability of choosing a red marble in the first drawing is 5 out of 7 because there are 5 out of the 7 that are red. Because the marble is not returned to the bag, there are only 6 possible outcomes for the second drawing. And if a red marble has already been chosen, the probability of choosing a red marble on the second draw is 4 out of 6. So the second of the multiplication rules of probability addresses the probability with 2 dependent events. So for this one, the formula would be probability of A times the probability of B, given that you did get A already. So an example, determine whether the events are independent or dependent, and then explain your reasoning. So first, we're just going to determine the difference between independent and dependent. Then we'll work with some dependent events. So one spinner is spun twice. Now, the spinner doesn't change, so these are 2 separate items. So this would be independent. Options, same. In a raffle, one ticket is drawn for the first place prize, and then another ticket is drawn for the second place prize. Since if somebody won the top prize, there's one less in there for the second drawing, so this would be dependent. And we would say no replacement. A random number generator generates 2 numbers. Generating 2 numbers, these are independent. There can be sample space stays the same. So once you pick a number, it doesn't take it out of the generator. You still have that possibility of picking that number again. Next, a basketball team is competing in the semifinals. If they win, they will play in the championship game. So this one is dependent. And our reasoning would be, well, you only move on if you win. So move on if win. B, a basketball player takes a free throw and then takes another free throw. Those would be 2 separate events. So this would be independent. Now one does not affect the other. Now in basketball, you could get, you might have the bonus free throw. So if you make the first one, you get the second one. That's reading too much into this statement. Just take the statement as is. So you're shooting a free throw and then you get the other free throw afterwards. Next one, a player has an injury and then has to see the team doctor. So this one would be dependent. And the reason for this one to be dependent is because you wouldn't go to the doctor the team doctor, unless you have an injury. So your visit to the team doctor is dependent on if you have an injury or not. Next, determine whether these are independent or dependent. Of the $100 that Ray has to spend, she wants to spend $59 on a blouse and $44 on some jeans. This one is dependent. And that one is dependent because what you buy first is dependent on what you buy what you buy second is dependent on how much you spent on the first one. So this is dependent. Second one, Ray asked each of the 3 store associates which handbag they prefer. Those are two separate events, so those are independent. And Ray purchases a handbag and a belt. Those are 2 separate ones. They don't affect the other, so these are independent. Now, the difference between A and C is A, there's a limit of how much Ray can spend. Letter C, there is no limit. Example 3, probability of dependent events. So it says the pizza that Jose and Tessa are eating has 10 slices and is half cheese and half mushroom. Tessa spins the pizza around and randomly selects a slice of mushroom pizza. If Jose spins the pizza and selects a slice after that, what is the probability that both he and Tessa selected the slice of mushroom pizza? So if there are 10 slices and they're half and half, Tessa spins and chooses a mushroom. So she had 5 out of 10 chances of getting a mushroom. Now there are only 9 pieces left over. And if Jose spins it, what's the probability that he picks a mushroom as well? Now there are only 4 mushrooms left. So that would give us 20 out of 90. Reduce that, and that would give us 2 out of 9 chances. Or you could put it as a percent. This would be 22%. Either one would work. Next, a gym teacher needs 2 students to be team leaders for a class of 12 boys and 18 girls. She randomly selects one student to lead team A, then she randomly chooses another student to lead team B. What is the probability that both team leaders are girls? So the first team, there are a total of 30 people. 18 of them are girls, so 18 out of 30 would be chosen for a girl. Now there's only 29 students available. 17 of them are girls. So if you did 18 times 70, or 18 30ths times 17 29ths, we end up with 51 out of 145, or as a percent, this would be about 35%. And our last question. On a math test, 5 out of 20 students got all the questions correct. If 3 students are chosen at random without replacement, what is the probability that all 3 got all the questions correct on the test? So for this one, 3 students are chosen, so 5 out of 20. For the first person, you have first chosen 5 out of 20, you have 5 out of 20 chances. The second pick would be, there's only 4 out of 19 left. And then the third pick, you'd have 3 out of 17. So if I multiply that together, 20 times 30 is 60. And then we have 20 times 19 times 17 gives us 6,460. I divide this by 60 over 60, so give us 1 over 114. Or if as a decimal, this would be, or a percent, this would be 0.9%. That is our lesson on probability and the multiplication rule.